She got her bachelor's from Penn State and her PhD from Madison, Wisconsin. And she also finished her PhD on Rickover Fellowship, so she spent how long at Bettis?
2 years.
2 years at Bettis Atomic Power Laboratory. So take it away, Rachel.
Great. So thanks for joining in this lovely summer day. Appreciate it. So I'm going to talk, I'm basically just going to give an overview of a couple of different research initiatives in my group. I'll talk first a little bit about what motivates me and who my research group is and where they are now. And then I think we're not actually going to get through all this, so we'll probably skip a little bit towards the end to give time for questions. But also feel free to ask questions as we go, and I'll try to pause in between each major topic area. So for me, I'm motivated by clean energy that works for the world. And so I think that nuclear energy is probably part of the solution. Almost all major studies out there say that if we're going to get to 100% clean energy, the last 30 or 40% needs to be a firm resource, and nuclear is the most viable of the things that are categorized as firm resources at this point. So I think a lot about how do we make new reactor deployment and existing reactors sustainable. So that is a lot of what guides my research and how I think about education. So what do we need to learn to think about new reactor deployment and existing reactor sustainment? And, maybe question mark, but that's the long-term goal, is to set people up to contribute to this mission. And so I do that by numerical methods. That's the stuff that I personally find interesting. And so to facilitate nuclear innovation, I used to say that we need predictive simulation. I think we're too far from that to really claim that that's what I'm working on. I would say I'm working on strategic simulation. How do we think about the quality of simulation that we really need to make the choices and get the information that we need? So to do that, I build tools. And when I say build tools, I mean I translate applied math into computer that other people use to design and analyze nuclear systems. I do not personally design and analyze nuclear systems unless I have to. I kind of hate doing that. I really like building tools and figuring out how the tools work and like saying they're good for things, but I do the things only to the extent that it reminds me that building good tools is important. Some of the work that I focus on is related to high performance computing. How do we use really big machines more effectively? Some of the methods I talk about will relate to that. Other methods are just sort of how do you make things work better on any computer. A lot of what we do uses the physics of the problems that we're trying to solve to inform our methods. That's kind of what differentiates us from applied mathematics. Applied math tends to be much more structure of the mathematics themselves. And because we're applied to a specific field, we can take advantage of knowing things about the field we're actually using. So knowing that this is what cross sections looks like determines a lot about the method choices that we make. So this is my group. This is the alumni role. So Richard is now a professor at Ohio State. I need to get an actual picture of Wei Zhang. He was a postdoc with me, and he did the Bay Area thing. He's at a software startup now. Madigan is a postdoc at the University of Illinois. James Bevins is a professor at the Air Force Institute of Technology. And Kelly Rowland is in research computing at Lawrence Berkeley Lab. And then Mario will be done in August, but I hooded him on Tuesday, so that's very exciting. April and Josh are going to graduate in about a year. I'm actually not talking about either of their work, really, but they do cool stuff. And then Mitch and Marissa are third-year students, and Sam and Vanessa are finishing up their second year. So that's them, and then what do they actually work on? So hybrid methods, I actually will talk a little bit about. So Kelly and Madigan both did their PhDs on hybrid methods for situations with strong angular anisotropies. I'll talk about Madigan's work. And Vanessa is doing that thing that we don't love to do that much, which is using those tools to do analysis. So we're looking at in reprocessing flow where you have holdup, can you use angular information to figure out where things are coming from to get a better sense of are things stuck in the system, whether they're supposed to be or not. More sort of generic deterministic methods. Mario does eigenvalue acceleration methods for the alpha eigenvalue problem. Wei Zhang really worked in finite element methods and sort of helped start that initiative in my group. And then while all of these people say finite element methods, there's much less work there than it sounds like because it's a really new initiative. So we're just starting in the finite elements world. But how many of you are familiar with the MOOS framework? So MOOS is sort of this multi-physics computational frame that takes all these different physics packages and couples them together, and it's finite element based. And so the motivation is to work on deterministic solvers that fit into that package, since that's where a lot of the multi-physics future is. And then what I call other adventures, these are all sort of one-off projects that are related to computation, but aren't their own like large research trajectory necessarily. So April's working in coupled neutronics and thermal fluids, so she's working on the pronghorn package. So we're really focusing on the neutronics piece, and it models pebble bed reactors, so both gas and then salt. Mitch has done pressurized water reactor analysis for his master's work, and we're now sort of doing some new work for me, which is looking at cryptography for safeguards. I'll talk about James's work first. He actually developed a new optimization algorithm to enhance experimental capabilities for neutron irradiation. And then with Richard, we did a lot of work in non-classical transport, which is when you have media that are distributed in ways that you have like long streaming paths and then clumps of interactions so that it doesn't follow the normal transport pathways. And that comes into play in pebble gas reactors, clouds. So we actually work with atmospheric transport people and image rendering people. So maybe the most fun part of that was getting to tour Pixar, because we collaborated with these image researchers. And so I'll give an overview of a couple of these research initiatives, but that's a sense of what everybody's doing. And what ties us all together is everybody's favorite, the transport equation. So how many of you are familiar with the transport equation? But not always. I mean, some people like. Anyway, so you're familiar. We're looking for where all the neutrons are. It's a balance equation. There are losses on one side and sources on the other side. And there are interaction probabilities. And when we have fission, we can solve it as an eigenvalue problem where we're looking for the dominant long-term behavior of the system. But figuring that out is really hard for some of the things that we care about. Some of the problems that we solve are very large. We can have, if you're trying to model a whole reactor, there's two dimensions of direction. We can end up with very large spatial meshes. Depending on what kinds of energy resolution we need, we can end up with very complex energy representation. If we're interested in feeding into multi-physics, then we need to care about what resolutions the other physics are and mapping into that. As we talked about, cross-section data is kind of a mess. And the ways that we solve this tend to be binned as deterministic and Monte Carlo, and I'll talk about strengths and weaknesses of those. And then this other thing called hybrid methods, where you use those two things together to try to take the strengths of each to defeat the weaknesses of the other. So Monte Carlo, you represent everything continuously in phase space, so you don't have to discretize energy. You might end up with geometry approximation sometimes, but it's pretty continuous. Conversely, in deterministic methods, that's where you add spatial meshes and energy meshes and angular quadrature, so everything's discretized. With Monte Carlo, the quality of your solution is 100% dictated by statistical error. So the number of samples that you take is directly related to the error. Whereas in deterministic methods, it's much more how you do the discretization and what numerical methods you use, so you get truncation error. For Monte Carlo, you have to specify what solution you want, so you get very localized solutions, so you have to be careful that you're asking for the thing you actually want. In deterministic solutions, they are global, and the solutions are of equal quality everywhere, and so that's an important piece coming up. Monte Carlo solutions are slow when things are optically thick, so for example, in shielding calculations, the whole point of a shield is to prevent particles to get to the other side. And so if you want to have enough samples to get a high quality answer, it's sort of the opposite of what a shield is supposed to do, so they don't work together very well. And conversely, when you have streaming problems where there's not much to matter for neutrons to interact with, if you're only looking down certain directions, you get very strong ray effects because nothing sort of spreads the neutrons out. Monte Carlo is kind of the gold standard. If you do it right, it is highly accurate. Deterministic, again, if you do it right, it can be very fast. And so both of those have their place. And so the idea of hybrid methods is to bring those two things together. And so for Monte Carlo, we do a thing called variance reduction. And that's where you try to reduce either the relative error or the computation time more quickly than the other so that you overall get a better calculation. So you augment how you play the game to play the game more smartly so you improve your solution. The ways that I'm going to talk about doing that is that you assign particles a weight, and the weight directly corresponds to the impact the particle has on the solution. And so particles can have weight at birth. If you wouldn't do anything to change your game, it would be 1, and it would stay 1 until the particle dies. But you can also change the weights of the particle as it moves through the problem. And then the whole sort of variance reduction world is about how do you do that? And so how do you determine what the weights are? How do you determine how to update the weights throughout the problem space? There are a bunch of different ways to do that. And the ways that we work on are called hybrid methods. And how do we measure improvement? So in a normal calculation, the relative error squared is inversely related to time. So if time goes up, the relative error will go down as the square root. So you can, if you are actually improving your calculation, the multiple of that will go up. And if you're not changing anything, it will stay the same. So that's how we compare. And in hybrid methods, we use deterministic results to make Monte Carlo variance reduction parameters. So what does that mean? So we take advantage of the fact that you can do coarse deterministic calculations really fast, so you're not putting a lot of computational investment in making these variance reduction parameters, and we're taking advantage of the fact that you get a global solution of equal quality everywhere, so that the information you're putting into Monte Carlo has a uniform distribution of accuracy. Because you can use Monte Carlo to make Monte Carlo variance reduction maps, but then you have statistical error of unequal quality in your variance reduction map, and that's its whole other thing. So we do this. And I will talk, maybe to motivate it to some extent, I'm going to talk about this cool optimization algorithm that we developed that is using hybrid methods as the engine inside, and then I'll talk about a hybrid method. But this one is actually using hybrid methods to design a real thing. So, and this is kind of up your alley, John. So when out there in the world, there are only, we care a lot about what energy neutrons are when we're trying to measure them or get them to do things. Neutron sources only come at very particular energies. And getting a neutron source that looks exactly how you want it to is not necessarily easy because neutrons are just born how they're born. And we can put a stack up of materials in between the source and the thing we're trying to do to change the energy of the neutrons. But cross-sections are sort of complicated. Figuring out exactly how you want to do that can be a little bit difficult because neutrons interact with materials in such strange ways. So our idea was to design an energy tuning assembly to do this material stack up. We're not the first people to think of this. This has happened before in the world, but it's really hard. So we wanted to make something that was a general purpose design tool so you could figure out what to put in the middle automatically. And so that was the goal. And so we started working on this general purpose meta-heuristic optimization algorithm, and we wrote a code called Quotient that implemented the algorithm called NOE, which are both like Greek heroes. But the software handles continuous and discrete variables, a complete set of search heuristics, and runs to nearly global convergence. And because we are using it to design an engineering thing, we don't actually care about global convergence. We care about getting pretty close because of machine tolerance and things like that, that the optimum is better than you can build anyway. And the key is that so we're doing a bunch of Monte Carlo calculations that are run in parallel. So what's the motivation? We were motivated by technical nuclear forensics. So when fission happens, the energy of the incoming neutron, so this is what energy is causing fission, determines a lot about what material you get out. So this is the mass number, and this is the yield. So if you have a thermal neutron causing fission versus if you have a 14 MeV neutron causing fission, you get a different distribution of mass products. And this is a couple of different elements you get out of all this. This is silver, this is barium, and this is samarium. Sorry, it's hard to read. But this is just showing what is the yield dependent on the energy that caused the neutron. So the idea is if you know what exact energy caused the fission, you can, or if you know exactly what fission fragments you have, you can back out what energy caused the fission. And so in the world of post-detonation nuclear forensics, people want to go like, if a weapon goes off in the world, you want to pick up the material and figure out where it came from. You need to be able to figure this out. People do training exercises for this right now, but they use a bunch of surrogate materials that are sort of cobbled together because we don't have real debris. So the goal of all of this was to make synthetic debris using an experimental facility so that they could do realistic training exercises. So we wanted to make an energy tuning assembly for this specific application, and then it's sort of demonstrating the process, and you can apply it to many other things. But the idea was we start with the NIF spectrum, which has a very high, everybody know nuclear ignition facility at Livermore. Big DT pulsed fusion. Anyway, it makes a large number of 14 MeV neutrons in a very short amount of time, and it makes very little other things. And so that is a great starting point if you wanted to get a thing that you could use for technical nuclear forensics. So our goal was to get something that contained a prompt fission plus thermonuclear spectrum. And so the goal that we wanted to put a stack up of materials to get from the NIF spectrum to this thing that is still a spike of 14.1 MeV neutrons and then this other distribution. So that was the goal. And so we're like, let's make an optimization algorithm to figure all that out. And we can, fundamentally in optimization algorithms, you formulate problems a few different ways. So sometimes you're just looking for a specific function. Sometimes you're trying to get your function to equal a specific number. Sometimes you're trying to minimize something. And you can classify optimization problems as singular, multi-objective, linear or nonlinear, constrained or unconstrained, continuous or combinatorial, unimodal or multimodal. And the design of an energy tuning assembly, so that stack up of material, is a single objective, nonlinear, constrained, continuous, and discrete multimodal optimization problem. So there wasn't anything we found in the literature that readily satisfied all of our needs. So we made our own. So what we were looking for was the spectra to match. So this vector is our stack up of materials. So we said it had to be radial in shape. So we had inner and outer radius, and then maximum, minimum height, mass, and density were the things that we were solving over. So we wanted the group-wise spectrum to match as well as it could. So this is the design, and this is the objective. So we run all these hybrid calculations in parallel. Each one spits out a design spectrum. We compare it to our objective spectrum and see if it fits. We also were planning to field this on NIFs, so that it has like a long-handled arm with a little cone at the end, so there was a weight constraint, so it couldn't be too heavy. So we needed the total mass to be less than the weight constraint. And then inside of our energy tuning assembly, we're actually putting a HEU foil to actually get enough fissions to see what happened. And so to get enough statistics for the radiochemistry folks, we needed a certain number of fissions. So we were also saying we had to get a certain number of fissions. So that was what we were shooting for. And we designed this algorithm, and we tested it against all these different engineering optimization problems. And so this thing, because right, you're looking to find the global minimum, so there are a bunch of different ways that that's hard. So we just looked at a bowl, this spiky thing. This one, you can't see it, but the spiky thing is inside the bowl. This is like a wiggly thing. This is a curvy, wiggly thing. and some engineering problems. And so there's a paper out there that lists all these results, but our algorithm outperformed almost uniformly all the sort of base algorithms we found published in the literature. So we compared across all these benchmarks to all these different algorithms, and we did well. So that was great. And then we actually designed an energy tuning assembly. We took out gases, we took out anything that was extremely expensive, and we took out anything that was too toxic to put into NIF, because somebody had to handle the device at the end. So with all of that, and then cleaning it up a bit for manufacturability, this is what we got. And with simulation, which I guess it's not out yet. We also have a paper that does all the nuclear data error propagation for this stuff. That'll come out in like 6 months maybe. But this is the objective spectrum, and this is the thing that we get at this little drawer that has the HEU foil and some activation foils. And you can see up in the place where most of the neutrons are, it matches pretty well. And it doesn't match super well down here, but there aren't that many neutrons. So we'll see. And then testing and validation, because this is the real important part. Also, by the way, as a computationalist, having one of my first students end up designing an experimental thing to run on NIF was like maybe not how I thought life was going to start. But it was actually a really valuable experience early on, because I had to think a lot about how do you tell if something's really right, what data matters, how do you design things for like manufacturability, how do we really validate it? So again, like not what I planned, but it was a really valuable early experience. So our long-term goal is to run on NIF, and we have been approved for 2 shots in 2019. We'll see if any of them happen, because we've been approved for a shot a year for the past 2 years. So we'll see. Fingers crossed. But fortunately, we have an 88-inch cyclotron up at LBL that is quite easy to get time on. So we did do some validation measurements at the 88-inch, where we got to run. We took a run with the whole thing, with every layer in between, just sort of do a deep dive on comparing what our estimations and what the measured data would look like. So we did get to do some of that so far. And then in the long run, we'll use what we found here and the NIF to get a better sense of how well we're matching. But overall, the idea is that spectral shaping methods like this can be widely applicable for turning the neutron sources that you have into the neutron sources that you want. And so there's another student working on this, expanding it to detector design is the first thing. And also you can imagine a bunch of health physics applications where instead of having to spend a whole bunch of time hand tuning and trying different materials, this thing just spits out a design for you. So that's pretty great. We've started some of the experimental validation, and we're hoping to get a shot on NIF pretty soon. And this is a picture of this, it's the device instrument manipulator. So the ADA goes way on this nose cone at the end. Any questions about that? That was kind of a long, I don't know. This was a really fun project.
When you define the way you define the cost function,
Mm-hmm.
the optimization,
Yeah.
is entirely about how close the spectrum, the design spectrum. But shouldn't you include also the attenuation, so you can potentially give up some of the spectrum, or you can weight the spectrum? There are parts of the spectrum
So,
that are more valuable for the specific application.
right. So we didn't use we did group weighting to get the largest magnitude based on group matching. We didn't do it based on interaction potential. That would have been a different way to do it.
How can you mix these is the question. Can you actually come up with a cost function that sacrifices one with different weights?
Yeah. You could.
Does your engine?
Yeah. You could make that modification. And right, you could put both and have it be like half of each or something. Yeah. We tried to make it pretty flexible. I think some of what we're doing now is trying to make it, so the cost functions you put in were pretty flexible. The Monte Carlo geometries it would let you do was less flexible, so that's what we've been trying to make it so that you can put in a wider range of geometry types. Mhm.
at some points. And another people were asking me, so why those cost functions and how do you justify them? And
Yeah.
I find it difficult to justify in general, not yours specifically.
Well, yeah, I don't know in general. I guess for us, because we're working on a specific engineering problem, right? So we needed a weight constraint because we weren't allowed to use it if it was too heavy. We had a fission amount, so we were like, what things do we have to get the answer that we want? We had a fission constraint because if we had too few fissions, the statistical error in the radiochemistry would be too high and our results would be meaningless. So like that was a hard limit. And then if our spectrum didn't match, we wouldn't get the right fissions. And so those were it was just, what problem were we trying to solve?
Did you have to adjust, or did you, let's say, hit the sweet spot right away?
Well, I mean, the cost functions were purely defined by what we were trying to do, right? So that it wasn't like it was just, this is how you define the question. So I guess what we adjusted was what materials were available. So it's not the cost function, but we realized like we shouldn't build this out of large chunks of platinum because we don't have the budget, things like that. Or we originally designed it with a material that Livermore was like, oh, we can't have that in our facility. So those were our iterations, much less than, the cost function was sort of fixed by the problem statement.
Okay.
Yeah.
So you don't have to go back to it, but earlier you showed the yield of several different fission products as a function of the energy of the neutron that produced them. Not talking about the saddle curve, but actually the ten-dimensional isotope. Did you get that from Freya or CGMF or some fission event generator?
Jeff.
Because INDEF really only tabulates it in a few energies.
And so it's, I think it's Jeff that spits out with the uncertainty bounds like that.
Well, that's cool.
Yeah, and we compared it to some experimental, the dots were literature values, and the solid line with the error bar was from Jeff.
Okay.
Yeah. Yeah.
Just wanted to hear your thoughts on the heuristic part of the algorithm, because some of the work that I've done, depending on how you integrate heuristics, whether to see the original problem or the intermediate that has the thought to kind of govern how the multimodal solutions don't get stuck in the local optimals.
So we used cuckoo search as the underlying sort of idea, and I might have a backup slide that has, So we combined a bunch of different heuristics together, yeah, and to help with the not getting stuck, we used Levy flights as our sampling strategy. Does that help?
Combining all of them can be quite effective.
Yeah, that's why you can handle a whole bunch of problems if you use a whole bunch of different techniques.
And is that interactive? Like depending on how the search is going, would you interactively change the search heuristically here, or it is all built in that it chooses its own search?
It chooses its own, but you could go in and tweak it if you wanted to. Yeah, it's not that tricky to comment, to add or subtract some of these options. Yeah. Okay. So thinking about making the actual hybrid methods, so we used hybrid methods there to get the design spectrum every time. But sometimes we want new hybrid methods, and I'm just going to start with all the clicks. So radiation shielding tends to be a tough problem, and it's extremely tough when there are strong anisotropies. So anytime you have narrow gaps or streaming materials embedded in moderators, it's really hard to capture that behavior with the deterministic code, and we know that Monte Carlo really struggles with shielding, and so you have to use variance reduction, but deterministic solutions don't work very well. So for example, this is a variance map where blue is low and red is high. of a PWR with a pipe going through a wall into a pump room. And this is what I like to call a beam of doom, where the error is too high that you can't actually tell if your solution makes any sense over there. So based on this error plot, you can't really tell someone if it's safe to stand in the pump room or not. So we would like to be able to capture the streaming behavior in a way that doesn't cause this effect. And right now, most hybrid methods are only a function of space and energy, and they don't include angular information very well. You could explicitly include angle, but then you have to have this giant variance reduction map that, because if you also store angular information, it becomes really huge. Also, sampling in angular space and making a weight map in angular space is kind of messy, and you have to do like interpolation across angles. And so then it becomes really expensive to use your variance reduction map. And this has been a field of research. We contribute to this, but I wouldn't say we have like the silver bullet exactly, but trying to find a method that is easy to use and works on many problems is tough. There have been some out there that work really well, but if you need a very large amount of expertise to use it, it's also not tenable for design solutions. So we decided to make our own. We've made 2 different attempts, and they work pretty well for certain kinds of problems. But the overall idea is that the methods that we're using use the adjoint solution to make an importance map. So how many of you are familiar with adjoint solutions to the transport equation? Some of you. So it's sort of like solving the neutron transport equation backwards. So this is a forward solution, and this is what you're used to thinking about, right? There's a source, there's a detector, the neutrons are near the source, and then you can see some of them go into this concrete, most of them don't make that turn. So that's kind of how we're used to thinking about it. So neutrons in the forward problem go from the source to the detector. So the adjoint is the opposite. So the adjoint measures how every part of the phase space contributes to the solution. And that is useful because now you sort of have a map of what the importance is relative to the solution that you're looking for. So given this detector being the answer that you want, the neutron, the like space near it is more likely to contribute to the solution at the detector, and this corner down here is less likely to contribute to the solution to the detector. Seems kind of obvious. It's not always as obvious as this. This is great for illustrative purposes, but it's not always, like you can't just make these by hand very easily for complex problems. So the adjoint is great because you can make these importance maps and then you can use them to make variance reduction parameters. The way that we do it most typically, or one of the most successful methods out there is called CADIS, the Consistent Adjoint-Driven Importance Sampling Method. And it uses the scalar flux, the adjoint scalar flux, to make a variance reduction map. Now, scalar flux is not a function of angle. The angular information is integrated out. So that's successful for a lot of problems. It doesn't work super well when you have strong angular streaming or strong space and energy self-shielding. So we wanted to update that method, but we were interested in figuring out a way to embed angular information in the scalar flux while still using the scalar flux, because then you don't have to rewrite all the software, you don't have to retool everything. It's kind of you can drop the solution in and everything else stays the same. So we made the scalar flux by weighting it with the forward flux. And so that gives you the shape of the forward neutron behavior without causing you to have a larger scalar flux adjoint that you're using in your solution. And so this has it's the best way to do it from a maximum entropy mathematical framework. We'll skip those details for now, but there are some mathematical reasons that this is a good idea. And the reason that we couldn't do this before is that computers weren't big enough to actually store and write the angular neutron flux for complex problems. Like almost all of the technologies that are developed in my work are just because we have bigger computers now, so you couldn't do them before. It's amazing what memory does. In fact, like most transport solvers don't even store the angular flux internally. So we had to update the code to store and read and write the angular flux. And so what happens is that you get angular information. Now, I didn't tell you this before because it kind of ruins the punchline. But this problem has vacuum boundary conditions. And so neutrons back here aren't contributing to the detector. Like there's no way for them to get back there. But if you're not including angular information, you don't know that. And so with our method, we now at least, it's not actually super likely neutrons from down here are going to contribute, but at least we know the ones that flew out the back aren't, right? So we have a much better set of information. And so we did a steel plate embedded in concrete, which is kind of a canonical shielding challenge, where we have a detector over here and a fission source over here. And we found better results. And that is good, because this problem is the one that motivated this whole thing to begin with. And I know this is a little hard to see. We ran the same number of particles for both problems. And this is the relative error as a function of energy. This solution is ours, which we called Cadus angle, and this solution is regular Cadus. And you can see the error is uniformly much higher for the same number of particles. But the thing you actually care about is the figure of merit. And so you can see the analog solution here had like quite low figure of merit. And Cadus by itself did do better, but our method was better still. And so it took a long time, but we got really low relative error. So you could trade those off. So we were pretty happy. And we did a bunch of toy problems that sort of characterize, it works for these kinds of problems pretty well. Okay, any questions about that stuff?
Let me ask a wider question.
Yeah.
Knowing that these solutions you could do this, suppose you know what output flux distribution do you want for these neutrons. Could you solve back and say, I could actually redesign my concrete or steel locations in the concrete, which may be more effective to produce what I have outside? And the reason I asked the prime question is because much of the cost in nuclear systems comes from concrete, and one reason it comes is because that concrete is basically, there is no concrete, there's all steel in there, trying to prevent neutrons from leaking. And we don't give any contribution to the shear strength of concrete simply because saying that there are cracks, the neutrons will escape. And so if that can be accounted for, it can save huge dollars in the construction or the reactor. So
Right.
thinking of that point of view, connecting the two things, that's potentially possible.
I mean, it would be really, if you wanted to do that, you would so that first method that was the optimization algorithm ran a hybrid method. If you had something where you cared a lot about angle, maybe you would use this as your hybrid solver. The other one was straight Cadus.
Right, but could you, knowing what you have on the outside, could you decide whether your steel plate should be, let's say, at a certain angle?
Yeah, I mean,
That way you could design your steel reinforcement there.
if you had an importance map that was relatively easy to look at, but it would be iterative, right? Because you would have to, but you could use it as a guide for sure. Yeah. Yeah. No. Good question.
How does this compare with the rate scalar flux, the joint scalar flux tool? You should have access to the angular moments of the flux.
Yes.
Potential.
Yeah.
Why would this be better than using tools? You know what I'm asking?
I don't know what you're asking.
So if you show that
Yeah.
expression,
Oh.
right? So you run discrete orders, for
Mhm.
example, and you compute sine,
Mhm.
sine bar A, dagger,
Mhm.
right? And then you apply this to get phi dagger.
Mhm.
But when you computed psi dagger, you should have access to phi dagger, phi 1 dagger, the angular moments.
Oh, I
that
see what
have
you're saying.
angular information already.
Right. Okay. So like, could we
How would
just?
that compare to this method?
Yeah. I
Because then
would
you're
have to
doing
look.
only one calculation, right?
Yeah. Right. So, like, if you would just say use phi 2 dagger or something because you knew you had strong anisotropy instead of.
All of them. I mean,
Yeah,
you have
yeah.
access to all of them.
You do.
kind of choose maybe based on magnitude, L2 norm or something. You figure out which is the most influential.
Yeah, we did not do that, but that's an interesting idea that you would maybe tailor it in each case. And yeah, to be fair, this actually makes more sense when you're doing FW Cadus where you're doing the forward calculation anyway. And so
Oh,
when you're doing CADIS, it does cost you the extra calculation. For FW CADIS. Yeah, but yeah, for FW CADIS, it makes more sense. But that, I want to go look at that. That's curious. It's a good idea. Okay, and then we'll get maybe partway through this. Actually, well, yeah, we'll get partway through this. So this is more like way in the deterministic methods part. So after we discretize for deterministic equations, we have this like coupled set of now everything is binned in space and energy and angle. And for each energy group, we have one equation that includes all space angular information. And we can write all of that in operator form, where we just write things as basically matrices. And so I'm going to go through some slides that uses this notation, where this is the streaming plus collision operator. This converts moments into angles. This is the scattering matrix. This is the fission matrix. And this is the basically reverse of M. And you can relate the angular flux to the scalar flux like that. So for Gauss-Seidel, so transport equation, there are a whole bunch of different solver types. Within each energy group, we use source iteration or a Krylov solver, something like that. When you go over energy groups, we can use Jacobi, or Gauss-Seidel is a more common one. A problem with Gauss-Seidel is that it can be slow when there's a lot of upscattering. So the transport equation is a series of coupled within group. If everything only downscatters, you just have a lower triangular matrix, and you can basically forward sub, and it's great. However, if you have low energy groups that kick neutrons back to the high energy groups, you have to like iterate over that until convergence. And so that makes your solver fundamentally serial in energy. However, so we can parallelize in space and angle pretty easily in deterministic equations. That's been done and done very elegantly. But machines are big enough now that space and angle parallelization hits an upper limit, and you sort of can't scale any farther. So we got interested in how do you parallelize in energy as well. And so that motivates this. And so the scattering matrix becomes semi-dense when you have upscattering. And so the Gauss-Seidel solution for one particular, so to get the new iterate of one particular group, you take the groups that have already been converged, so the higher energy groups, and you use the new iterate, and then the groups that haven't converged yet, you use the past iterate because you haven't iterated over them yet. But now you have information from two different iteration levels, and it's what I just said, you can't parallelize in energy. So we wanted to do something different. So Krylov methods have pretty strong convergence properties, and we can do when I started this project, we could do Krylov methods over one energy group, but we were interested in doing it over multiple energy groups at once. And so basically, we solve the downscattering block like normal because it's lower triangular, and that's easy. And then we move it over to the right hand. So this now part of the block dense part of the matrix is operating on groups that are already converged, so we move it over to the right-hand side. And then this thing is what we call the upscatter block. And so we use a Krylov iteration vector that contains all of the groups that contain upscattering. And we can solve each of these rows on a different set of processors. So they can iterate within their own group and then communicate periodically. And so now you can parallelize in energy to the degree that you have upscattering. And that, again, this is one of these, like, it's sort of silly, but the whole reason this method became possible was because we had memories that were big enough to hold multi-group size iteration vectors. And that was previously the limiting factor. So we just couldn't do it because memory's big enough now, so that's great. In addition to this thing, so this was great because it allowed us to solve multi-group problems more quickly and scale to larger processors. We also wanted to tackle the eigenvalue part of the problem solution. So power iteration is one of the historical methods that people have used. They're finally starting to move away from it because we have some other methods. But you basically, you do this over and over again, and your error goes like the second eigenvalue over the first eigenvalue, and if they're close together, your error reduces really slowly. And that happens quite a lot in reactor problems, especially when you have a lot of scattering. So that's called the dominance ratio. When dominance ratio is close to 1, your convergence slows way down. So you can do a thing called shifted inverse iteration. And if you take some shift and apply it to the identity matrix and subtract it from your A matrix, you have the same eigenvectors, which is sort of the key that makes this all possible, and you can relate the eigenvalues of the shifted system to those of the original system. So these are the original eigenvalues, and it's the inverse with the shift subtracted. And so why we care about that is that if the shift is very close to the first eigenvalue, it becomes separated from the others. So as the shift approaches this dominant eigenvalue, this thing becomes much larger than all the other terms, and the convergence speeds way up. So now the convergence ratio is this thing that is getting larger over this thing that is not as large. You can have a fixed shift. You can update the shift every iteration. That's called Valence method. And what we did was implement the Rayleigh Quotient iteration. And
So
yeah.
You choose the shift?
Yes, you choose the shift. Or you can,
Just eat some cherry, or what do you choose?
there are a whole bunch of different strategies. I mean, normally you're solving for a nuclear reactor problem, so you usually would pick something close to 1. But there are update strategies that play different games, sometimes like 1 plus or minus an epsilon. What we did was this thing called the Rayleigh Quotient, where you calculate the shift every iteration. So the Rayleigh Quotient, if your eigenproblem is formulated like this is the Rayleigh Quotient. So if x is close to an eigenvector, then the Rayleigh Quotient is close to an eigenvalue, and it's the best guess in a least squares sense. So if x is actually an eigenvector, then the Rayleigh Quotient is actually an eigenvalue, and then it's the best guess. So it's basically the best guess you can make. And so we use the Rayleigh Quotient as the shift. But if you sort of look at how this is, we are now taking the scattering matrix that was semi-block dense, and we're now making it fully block dense because the fission term, or the fission matrix has terms everywhere. And so we are, from how it looks, we're like functionally putting up scattering in every group. And so if you were using the Gauss-Seidel method that doesn't handle upscattering very well, that would be too slow. But now if you have this Rayleigh Quotient, or this Bloch-Krylov solver, you can handle having this block dense scattering matrix and parallelize in energy, and everything works just great. So that basically Rayleigh Quotient iteration became a reasonable idea because the Bloch-Krylov solver existed, so you could deal with this like upscattering looking thing. So that was great. However, I said all that. The problem with when you have a shift that gets really good is the condition number of your matrix gets really bad. So your matrix becomes, so the better your shift is, which is what you're trying to do, the worse your condition number is. And so then your solver starts having a harder and harder time. So you need a preconditioner. So we couldn't get this to converge for most problems that were interesting at all without a preconditioner. So we wrote a preconditioner based on the multi-grid method. And so in a fundamental sense, the multi-grid method, iterative solvers are good at removing oscillatory error modes, but they are not so good at removing smooth error modes. And so the point of a multi-grid method is that you take your solution and you map it to a coarser grid to make the error look oscillatory. And then you iterate to remove that now oscillatory error mode. And so you map from a coarse grid to a fine grid, and now you iterate on there because it looks like it's oscillatory, your error goes away. And then you map back to the first grid. So you have this correction. Basically, you're removing different error modes at different grid levels. And so you can have 2 levels, or you can have a whole bunch of levels, and you can do fancy looking cycle patterns. But we implemented the multi-grid preconditioner in the energy dimension. And again, this was a thing that you didn't do before because of how we handled energy groups. But if we have the Krylov solver, it all becomes pretty easy. Also, it's easy to linearly, it's just easy to collapse and expand in energy. It's 1D and it's linear. And we used the iterative scheme that we used at each level was just the weighted Richardson method because it was fast. And we had to play around with how deep is the V cycle and how many relaxations do you do each level and what's this weighting value. And we have some suggestions for reactor problems in our paper. And then we tried it out on a couple of really big problems. So we did a large PWR that had some different fuel enrichments and pretty decent spatial discretization. We only did P0. We used S12. And so we had this like very large number of unknowns. And we solved, so we divided the 44 groups into 11 energy sets. So each set of processors had 4 energy groups to solve. Wrong one. And we used about 140,000 cores for these results I'm going to show. And we found that Rayleigh quotient iteration was faster than power iteration. And so this was with a few energy sets. This was with a lot of energy sets. Power iteration with a preconditioner was not able to converge the problem. Rayleigh quotient iteration was, and it was faster. And then we did this other thing where we used a reduced quadrature set inside the preconditioner, because the preconditioner needs to just be like kind of roughly making things better. And so using S2 instead of S12 worked just fine, but was a heck of a lot faster. So that was useful. Then we compared this same thing with a slightly different configuration of the preconditioner and trying power iteration without the preconditioner, where we learned power iteration doesn't need this preconditioning, it makes it too slow. But Rayleigh quotient iteration with preconditioning worked great. It also scales really well, so we ran our problem with increasing number of energy sets. This was perfect scaling, and this was our scaling. So way out here it gets a little bad, but we're at like 1 million cores out there. So it did pretty well. And then we tried another problem, because we wanted to make sure it wasn't just that one. So we did a PWR, and we did a Babcock and Wilcox benchmark problem. This one was a little bit smaller. We tried 425 million unknowns and a smaller number of cores. And we found our method worked the best when we had high parallelization. So before I was comparing to power iteration, Arnoldi is a Krylov solver as well that you can use as an eigenvalue solver. It's better than power iteration, so we were curious how this all worked. And so Arnoldi, when you did the energy parallelization across all the energy groups, was the slowest. Arnoldi, where you only parallelize the upscatter groups, is fast when you don't have a lot of energy parallelization, but it doesn't scale as well. So Rayleigh quotient iteration with the preconditioning performed the best with high groups. If you have low parallelization, use Arnoldi. If you have high parallelization, use RQI. And then we did a bigger version of the problem, and we got the same performance, just on more cores. And so this was useful in, basically we found that if problems were not huge and were not very hard, you should use power iteration or Arnoldi. But if problems were very large and difficult, you should use Rayleigh quotient iteration with this preconditioner. They were kind of big guns, so if your problem isn't that hard, you don't need them. And I think I've said all that. So yeah, Rayleigh quotient iteration is an optimal eigenvalue method when you have these loosely coupled systems or where the first and second eigenvalues are close together. Needs preconditioning, works for challenging problems. You can do it because of this Krylov multi-group solver and the preconditioner. All right. And then the only thing I'm going to say about this, we're working on a new code called BART. And Yeah. It's, no, there are new BART cars. They're amazing. They're brand new. Anyway, there are a couple of new BART cars. They're like beautiful. Yeah, I think they're just easier to hose down. But the real thing that I'll tell you, and then we can, because this is the interesting part. So we wanted to make a framework that it was really easy to investigate a bunch of different methods. So it's built from a very like C++ sort of atomized unit frame with a high level of polymorphism, so that it's like the most kind of abstract concept of how you would implement different methods, so that when you want to add something new, you can change the minimal amount of code possible. And we're instrumenting the code so that you will get a lot of comparison data, so that if you, basically you will tell BART, run this base method and run my new method that has not required very many code changes to implement, and it will spit out all this data of how it compares, so that you can learn a lot more about what your methods are really doing and why it was faster and why it was slower. Because you're not comparing two different codes, you're not comparing a code that involves some like huge amount of code change. It's like, yeah, it's a very granular instrumented research tool. And so we're like in the middle of that. So, and then there's math about what we did first, but we're kind of out of time. So I'll leave it there. So thanks for your attention. Are there any other questions? Yeah. Everybody asked already? So I ended somewhat abruptly. I also spend a lot of time thinking about how in an academic research environment do you write high quality software, because it's really easy to just try to get results for your dissertation or for your paper or whatever, and you write this like spaghetti horrible code that you're not totally sure it's actually producing the right results. And then you graduate and you leave and you don't answer your advisor's emails ever again, and no one can use your code. And so all of this like lovely science just sort of doesn't ever contribute. So it is somewhat slower, but it's faster overall if you write sort of version-controlled, tested, documented code. And then your science gets to live on and keep contributing to the future. Like James's project, I actually hired him as CS undergrad to help with all the computer science pieces, so that now there's a grad student who can keep working on that code, because like it was easy to use. Anyway, that's my public service announcement for the day.
Thanks again, Rachel.
Yeah, thank you all. Thanks.